Let's now solve manually an example for the most simple case when we have a line, a polynomial of the first degree. So what is our data? 10 random British drivers were chosen, and for each driver we know years of his or her driving experience, that is xi, and monthly insurance premium, that is yi. So x's are 6, 3, 11, 10, 15, 6, 25, 16, 15, and 20. And y's, insurance premium in British pounds, is 66, 88, 51, 70, 44, 56, 42, 60, 45, and 40. So, and we want to construct a linear regression model. So we say that yi is theta 0 plus theta 1 xi plus epsilon I. So we use the model of the first degree with just two coefficients, theta 0 and theta 1. And so we need to estimate theta 0 and theta 1 using the OLS, ordinary least square method. So we assume, to use the OLS, we should assume that our observations are normally distributed. It's more accurate to say not the observations, but the random errors. So we say that, so let's assume that random errors are independent, identically distributed, and follow normal distribution. So that they are independent and follow normal distribution with zero mean and the same variance. So after this assumption, we can apply the OLS. So, and what formulas should be used here? So as here we have this simple case with a linear function. So as we assume that y is a linear function of x, then it's better not to use this general approach, either with matrices multiplication or not to derive the formulas for the theta hats directly by differentiating the sum of squares. But it's better to use special formulas for this case, for the polynomial of the first degree. So let me remind you these formulas. We know that theta 1 hat is mixed sum of products of x and y, minus n times x bar times y bar, divided by sum of squared i's minus n times squared x bar. So this is formula for the theta 1 hat, and as for the theta 0 hat, we have y bar minus theta 1 hat x bar. So as you see, to apply these formulas, we need x bar, y bar, sum of squared x's, and sum of products of xi, yi. So I have already calculated figures for these auxiliary stuff. So in our case, x bar, so that is 1 over 10 times 6 plus 3 plus etc. up to 20. So x bar is equal to 12.7. Y bar, that is 1 over 10 times 66 plus 88 plus up to 40. So y bar is equal to 56.2. Then sum of squared x's is 2033, and sum of xi, yi is 6402. So after we have this, we can substitute to the formulas for thetas. So we say that theta 1 hat is 6402 minus n, that is 10 times x bar, 12.7 times y bar, 56.2, divided by sum of squared x's. Oh, I have forgotten the square here. So 2033 minus 10 times x bar squared times 12.7 squared. And after doing all necessary calculations, we can see that this is equal to approximately to minus 1.75. And then theta 1 hat, theta 0 hat, I'm sorry, is equal to x bar to y bar, 56.2 minus theta 1 hat times x bar and this is approximately 78.43. So finally, we see that our model, our regression model, is that y is equal to 78.43 minus 1.75x. So this is our model. We can use hat for this y, as we can say that this is the predicted y. So this is not the actual y, but this is the y that can be predicted with our model, with our regression model. So this is the, so what we have just got? This is the formula that can help us to predict the average monthly insurance premium if we know the years of driving experience of a random driver. So if someone tells us, so I know a driver and I know that he has, let's say, 13 years of driving experience, of driving practice. So can you tell, what do you think, what about his insurance premium? And you can say, okay, I will substitute this 13 for X to this formula. And so with the help of this formula, I can predict. So I can say that I suppose that his monthly insurance premium is about, and so then you tell what you get with this formula. You tell y hat. So this formula can be used for predictions. So if you want to estimate unknown y when you know x, you can apply the formula. Now let us have a look just how this can be if we graph what we have here. So what we have, actually we have observations. Observations are 10 points, and we have the model. The model is the line, so this graph of this function, of a linear function, is a line. And so approximately if we graph all this, we'll get a picture like this is not the accurate graph of these 10 points, so it's just an illustration approximately how all this looks like. So the graph will look like this. So there are 10 points, there is a line. We see that slope is negative, so this coefficient at x is negative. And it's obvious, just the more years of driving experience one has, the less his or her insurance premium is, obviously. So as more experienced means more careful, more maybe not more careful, but so the better, the more experienced the driver is, the better his or her driving skills are. It's better to say so. And so the less the risk of a traffic accident is. So, and here we see that, yes, it looks like that linear model is quite good for this situation, that it fits the data and describes this relationship, describes this dependence between x and y accurately. So, for example, if we see, after applying this linear model, if we see a graph, let me say, of this kind, so for example, these are observations, and so this is the model. If we see something like this, if we saw something like this, we would say no. So the model does not fit the data. We see that we see something like a kind of a parabola, and we are trying to describe this situation with a line. So this would mean a picture of this kind would mean that polynomial of the first degree is not sufficient. It's not enough. that we need a polynomial of the second degree, at least, to describe this relationship accurately. But in our case, for these data, for these observations, we will see a picture of this kind, and so it tells us that linear model is quite enough. So that is how, just after applying a regression model, we can just have a look to understand if our model is good enough or not.